Okay, in this part of the fluid mechanics unit, we're going to be talking about buoyancy. And buoyancy is an upward force on an object in a fluid that is caused by the weight of the fluid displaced. Okay, so let's say I have a beaker with some liquid in it, and then I take and I drop in a solid that's going to float in the liquid. What's going to happen is it's going to displace some of the liquid, so the level is going to go up some. So this is the displace volume. And that water, the weight of that water is going to push back down, which will push up on the block that's floating in the water. So the equation, the force of buoyancy equals the force of gravity on the displaced liquid. Okay, because you remember, weight is the force of gravity. Now, for the force of gravity, it's going to be the mass of the liquid displaced times g. Now, for the mass, we can do density times volume. So this is the way that it is written on the reference table. But we have to remember that we're doing it for the displaced liquid. So rho equals the density of the liquid that it's in. And V is the submerged volume. Okay? Because it's only the part that gets displaced, so only the part of the block that is in the water is displacing liquid, so that's the volume we have to use. So here's an example. A metal cube is 1 centimeter on a side and has a density of 7,000, and we want to know the mass and the force of gravity on it. So we're going to start out with this. We have this thing that's 1 centimeter on the side, which is 0.01 meters. Okay? And we're going to have to find the volume of it. So the volume is going to be 0.01 times 0.01, which is 1 times 10 to the minus 6 meters cubed. Now that I have that in its density, I can find the force of gravity. Now I'm going to do it a particular way. It's going to be mass times g. For mass, I can do density times volume. It's the same formula as the buoyancy force, but this time I'm finding the force of gravity on the solid, so I'm going to use the density of the solid and the volume of the solid. So the density was 7,000. The volume is 1 times 10 to the minus 6. G is the acceleration of gravity, or 10. And we end up with a force of gravity of 0.07 newtons, their force of gravity. Now, part B, the cubes are submerged in water, and we want to know the buoyancy force. Okay? So now, for buoyancy, we're going to do FB is rho, VG. But this time, it's the weight of the water that's displaced, so I'm going to use the volume of the liquid times the volume submerged. Now, in this case, the volume submerged equals total volume because it's completely underwater. So now, FB is going to equal the density of the liquid. It's water, so we know that's 1,000. The volume is 1 times 10 to the minus 6, so the entire cube is submerged, and then V is 10. And that's going to give us 0.01 newtons for the force of buoyancy. Now I want to find the acceleration. In order to find the acceleration, we're going to have to draw a free body diagram. So here's the cube in the water. We know it has a force of gravity down on it of 0.07. And it's a buoyancy force of 0.01. Now, we also know that its mass, if the force of gravity on it is 0.07, its mass is 0.007, which is divided by 10. Now I have my complete free body diagram. I'm trying to find the acceleration. So I would do an F-net equation. So F-net equals M-A, 0.07 minus 0.01 is 0.007A, 0.06 is 0.007K, and that'll give us an acceleration. 8.57 meters per second squared. Which makes sense because if it wasn't the fluid, it was just falling at 89.8, it's going to go a little bit slower as it goes through the liquid because of that upward buoyancy force. Our next example, we have a piece of wood with a density of 600. Its density is less than the density of water, so this one's going to float. And we want to find out what percentage or what portion of it will be submerged when it floats in water. So I'm going to draw a little sketch over here. I have my beaker. All right, here's the liquid. I have the thing floating in the water. And I'm going to call this volume down here the submerged volume. And we're trying to find that, basically. Now, we can find the force of gravity on it. It is M times G. Now its mass is going to be its density times its volume. So we do density times volume times G to get the force of gravity. Now I'm finding the force of gravity on the whole block of wood. So I use its density as 600 times its volume. We're going to call that B, the total volume, times 10. So I get 6,000 V. Now I want to find the buoyancy force. We always use rho Vg for the buoyancy force, but we have to remember it's the density of the liquid and the volume submerged. So it's 1,000 for the liquid because it's in water. Okay, V is going to be submerged volume this time because for the buoyancy force, I only want to use the volume that is displaced, and that's only the volume that's submerged below the water. And that times 10. So that's going to be 10,000 to be submerged. Now, since it's floating, it's not moving up or down. I know that FB has to equal FG, because if I was to draw the free body diagram of this, I have FG down, I have FB up, and they're going to cancel each other and it's going to float. So I can rewrite this as 6,000 V is 10,000 submerged. Now, I'm trying to find the fraction, so I want to know V sub divided by V. So it's kind of like reverse cross multiplying. I'm going to take the V and put it on the bottom over here on the right, so I get V sub over V. And I'm going to take the 10,000 and put it on the bottom over here. So 6,000 over 10,000, which is 0.6, which tells us that 60% of it will be submerged. Now, there's a trick to doing this. All right, I'm going to write that above. The trick. The percent submerged is going to equal the density of the solid divided by the density of the liquid. So we could have done that shortcut. We could have done 600 divided by 6,000. The density of the solid is 600. The density of the water is 6,000. I'm sorry, it's 1,000. 600 divided by 1,000 is 0.6. So the percent submerged is 60%. But you need to be able to be drawing these free body diagrams and finding gravity and buoyancy forces. So this was a good example of that. If you don't remember this trick, you can always go back to this method to solve it.